I'm happy to introduce our next speaker. Felix is actually an expert in everything related to industrial control systems, SCADA, with more than 9 years of experience as a researcher for Lime Security. Working in the critical infrastructure, working for the energy sector mostly, and really diving into everything related to industrial and control systems and the security around. He's here to again explain to us why this is important. I'm sure for everybody it agrees that electricity is important and energy as well. So we're more than happy to have him. A warm round of applause, please. Thank you.
Okay, mic check. Okay. First I want to thank the organizer for letting me do this talk, to finally talk about something that really pains me. And that is building binaries for all kinds of weird embedded platforms. Like when you do OT, when you do embedded pen testing, you see all kinds of rare CPU architectures. And when you need tooling, you're probably out of luck. And I wrote a tool called Sthenos to help with that. So I'm from Lime Security. I'm doing vulnerability research, and basically we're a company located in Austria. So we do a lot of OT pen testing, consulting, and trainings. And in my free time, I'm writing a blog and some open source tools, like Sthenos. So many modern embedded systems nowadays run on Linux. In the OT environment, you often see some other operating systems as well, like VxWorks or QNX, or some proprietary stuff, or sometimes just R2S with bare metal operating system. But Linux is becoming more and more prevalent. So even SCADA systems that used to be proprietary operating systems are now based on Linux. And during most assessments, we get some form of shell access to the systems, either intended or unintended. And then we want to do some further analysis. And static analysis is often tiresome and often not very efficient. So dynamic analysis, like for example debugging, or for example doing function library calls or tracing function library calls, is the way to go if you want to dig into systems fast. And an alternative approach would be to emulate the systems. However, emulation of the systems is often difficult and tricky and not possible at all, because like they have custom I/O ports, they have some extensions that you cannot emulate properly. So emulation of the software is often not possible. So the best option you have is bring your own tooling to the target platform, and that means you have to build your tooling yourself. And who has used GCC to compile a tool before? Okay, who has had some major GCC errors and spent some hours debugging this? I see some raised hands there. Okay, so I'm not the only one here. And normally embedded pen testers and OT pen testers need this kind of tooling. But I have a few friends who are doing red teaming, and I was quite astonished that they also need these tools, because they told me, hey, we're moving away from classic Windows clients to persist. We are trying to persist on, for example, routers or NAS systems that are in the customer networks, because there is no EDR, there is no CM on the systems. So they try to use these blind spots in customer networks to persist. And that's where they ran into the same problem. Now they need tools for these platforms. And sometimes it's just nice to have them to debug stuff. So normal engineers could use these tools as well. Okay, but why is it so hard to build these tools? And that's, for example, one example why it's so hard. Because sometimes you have architectures like, for example, MIPS. Okay, most people know MIPS. But then it's a 32-bit version of MIPS. It's a V2 instruction set, it's big endian, and a soft float support. So if you compile anything is wrong on this, for example, if you use hard float support, you're out of luck. Your binaries do not run on this. So in general, getting the correct architecture with the correct API correct is kind of a pain. And a good example of this is, for example, floating support, which is kind of one of the main CPU extensions that is being used to compile this, or is being used on these systems. And the floating support basically tells the compiler that it has floating support in hardware, so there are certain assembly instructions. Like we see here on the example here, this is an example without floating support, so it just loads, this is a MIPS assembly, and just loads the value A and B into some registers, and then calls a normal function to just do the floating operation, and then moves this moves the result into A. So, but this soft float implementation is just the implementation in assembly. It is rather slow, but if you do not have hard float support, this works also on hard float environments. A little spoiler here. Okay, so in general, then when you have hard road support, for example, on the bottom you see like there are certain registers like F2 and F1. They are only there if you have floating support. And there's also a certain assembly instruction to do floating operations. And the funny thing is, you can execute, for example, a MIPS binary that has hard float and a soft float architecture. It will run until it hits a floating operation. So if you're lucky and you do not use a floating operation, it might run sometime. But then you get an illegal instruction and the binary just crashes. And there are also other hardware extensions that are typically for certain platforms, like for example, when we have crypto acceleration, or for example, certain registers for vector operations that can be optional. So when you build the tools, you have to keep this in mind. It's just a pain. It is just a pain to do this because at some point you think, I have the correct binary built for the target platform, and then at some point it just crashes because you forgot, hey, this doesn't have this CPU extension. But that's not where our problem ends. Even if we find the correct architecture out, we still have to find a libc library to build our libc code. Because libc provides us a standardized interface, so we do not have to do syscalls ourselves. If you are such a mad lad and just do syscalls yourselves, good luck, you probably do not need glibc or any form of libc, but your code will probably not be very portable. And when it comes to user space, there are many different implementations of libc variants. For example, there's glibc, musl, diet libc, and microlibc. And all these libraries have different functions, so they all have a common set of functions, like the POSIX standard, but they have certain properties. And when you want to dynamically link these libraries, you have to match them with the target platform. So, for example, if you want to build a binary for your router that has, for example, glibc, then you also need to have a glibc binary. And this is especially tricky with glibc, that glibc has different versions and they're not compatible with each other. So if you link it for the wrong version, you're out of luck. And on better systems, sometimes they have weird linker paths. So if you want to run a binary, first the linker loads it and then it's being executed. So, and if the linker path is wrong, it also doesn't work. But this can be easily patched with patch 11. So, and the next issue you have, you need to find a toolchain for this. So you need to find a GCC variant, or you need to compile GCC yourself, or the libc yourself to run this. And for most architectures, there are already pre-built build chain for this, which is quite nice. And however, if you want to use, for example, more powerful compilers like Clang or LLM, these compilers do not support all architectures that well. So GCC is, in my opinion, the best compiler for most architectures, because it supports so many of them. Okay, and the problem is this gets even more complex if you build tools that have a lot of dependencies. So for each dependency, it starts again. So you have to, for example, if you want to compile tcpdump for your portable hacking tools, you need to include also libpcap or some optional dependencies. So now you have to compile libpcap first and also have the source code adapted to the target platform. And so this repeats and repeats until you have a full binary that works with this. And if you dynamically link this, you also have to bring all your libraries on the target platform, which is kind of tricky because then you have to put them into the library path, in the LD path, and then to be loaded from there. Yeah, and in general, this isn't probably not good for your Penance project because it tends to use a lot of time to compile these tools. And also, if you do this in your free time, it probably will take a lot of time to implement this and correctly get the tools to build. So the oldest trick in the book is just to say, hey, I want to statically compile this for this target platform, and then you're good to go. So static compiling is just where you just take all the libraries and also the libc functions and just build one static portable binary for the target platform. And the pro is you have no version conflicts. It runs on any architecture with this, on any Linux system with the same architecture, and it's generally easy to port around. So once you have a build chain running for this, you can just swap out a compiler for a different architecture, and then you're good to go. The only downside for this, you get rather large binaries. For example, if you compile tcpdump or other tools statically, you might have a binary, or for example, curl is a good example. you might get a curl example, a curl binary which is multiple megabytes. And for embedded systems, multiple megabytes sometimes isn't feasible because there is no storage for multiple megabytes binaries. Okay, and there have been many attempts out there to build such a tool that is universal and easy to use. For example, the most famous repository on GitHub was, at least what I found on GitHub, was from NGD, static binaries, 3.5K stars on GitHub, which has good support for multiple architectures, but is was last updated 8 years ago. And it lacks support for many of these architectures that are now for modern architectures like RISC or Long Arch. And there are also other repos out there, for example, SOA packages, which is a cool repository for Linux packages, but they also do not support most of the architectures that are being used out there. So there are all these tools and all these approaches, but there isn't like a dedicated tool for all these architectures that's easy to extend. And that's why I wrote Sthenos. But first, let me talk about which kind of libc to use when you want to statically compile stuff. And the best choice here, in my opinion, is Muscle, because Muscle has a small footprint, it is very portable, and it is POSIX compliant. So it works with many tools, but not all. And glibc is sometimes needed for some tools, because you have the problem that some tools use custom functions that are only available in glibc and not in Muscle. And so the approach of Sthenos is basically to use Muscle by default and then fall back to glibc to build binaries. Okay, here's some facts about this. glibc is basically the oldest library around. It was the first GNU library for the libc, replacing the libc from Solaris, or being an alternative to. And it's generally ported to most of the architectures. So glibc is running on most CPU architectures. And it is fully POSIX compliant, plus has some extensions, like I already mentioned. And it has a lot of legacy code in there, so it's a bit larger than the Muscle. Muscle is a bit newer, and its general is POSIX compliant and is more smaller. And here, for chart, for example, a simple hello world, for example, takes like when you compile it with dynamic, it's just a few kilobytes without any optimization. With Muscle, it's about 20 kilobytes more, and it depends a bit on what functions that the target tool is using. The more functions included. And if you just compile this hello world statically with glibc, you're suddenly at about a half a megabyte. Which doesn't sound much, but if you have a lot of tools and you use a lot of glibc functions, your whole toolchain will get a lot larger. Okay, so let's talk about Sthenos. So Sthenos basically puts all this stuff together in a single tool. It supports about 50 CPU architectures, the counting variants, for example, MIPS are 10 variants. And it can compile two things. It can compile static binaries, and it can compile shared libraries. And for example, if you have, for example, exploit, you need to compile for different architectures. That's pretty useful if you can compile it one time, maybe just as an exploit, as a binary, or just as a shared library, which can be, for example, used by LD preload or other tricks. And it also includes some of the more common tools I use, for example, gdbserver, strace, ltrace, and so forth. So the name for the region was basically, in Austria, there's a second cybersecurity company called Cyberdanube, and they had a similar idea. They called it Medusa Embedded Toolkit, but they just published the binaries. And I was like, hey, can you release the source code for this? I created a GitHub issue, but they didn't respond to this. And I was like, guess I have a weekend time, so I can build this toolchain myself. And that's why I created Sthenos, to have a more open source and just something you can build on yourself, because you cannot just download binaries from someone on GitHub and run it on the target platform of the customer. And generally the goal is like this. You take Sthenos, just run it, and you're good to go. And instead of doing what's below there, it's just jumping all the hoops to just get one static binary from one architecture. Okay, and here are some examples of the architectures supported. These are like more common architectures, and also some old architectures, like for example Spark or older MIPS architectures. Okay, so why is this tool different from the tools that are existing? Well, it makes it easier to choose between libcs. For example, if you have a tool that needs glibc, you can just select it, and it's easy to build because it's very portable and it's based on Docker. And it's quite easy to adapt to new architectures, so you just have to include a new compiler and a new libc environment, and then you're good to go. And it should be quite easy to add new tools to your toolchain as long as you can compile it with glibc or muscle. Okay, and the majority of the tool is basically based on bash script. I have chosen bash script for a reason. It is quite, when you have build chains, you often work with environment variables that influence, for example, what compiler is being used and what flags are being used. And to make it a bit easier, bash script is kind of the best way to go about this. And it also builds in Docker, so it doesn't mess up your host system and to keep the thing portable. And it has a caching and a download feature. So it is like if you build for a toolchain the first time, it just downloads the toolchain and then it caches the toolchain and also caches dependencies. For example, if you want to compile multiple tools with OpenSSL, it caches the OpenSSL library and then can reuse it for multiple tools. And since, I think it was last week or the week before, there were news broke about some NPM packages that have been compromised due to supply chain risks. I already pinned all dependencies in the tool to mitigate supply chain risk a bit in this tool, because it downloads basically source code from all kinds of sources, and it verifies if these packages are still the same packages. So you do not need to worry about this. So, but enough talk. Let's take a look at how does it work. Okay, so, but first maybe just start at GitHub. So on this GitHub page, basically, the tool is just open source, and I made a special BruCON release, and here you can basically download all the precompiled binaries already for different tools. For a target architecture, you see there's a long list of target architectures supported. And these are also available when you check out, for example, in the output folder, you see, for example, there the binaries just as a single binary. But if you say, hey, I don't trust the binaries you compiled, I want to compile it yourself, you can just download the code and run it. And that's quite easy. So zoom it in a bit. Is the font okay in the back? Okay, seems good. Then let's enter here. So basically, the code is mainly in the build file, and if you want to use this, you can just use the build option with -help, and then you see there are some predefined tools in there that you can just compile for different architectures. For example, strace, busybox, and I will talk about them later on. And there are also like different libraries you can just compile automatically with this tool. And if you want to compile something, you can just write the tool what you want to compile. For example, if you want to compile nmap for the architecture, and then mistype this, and then you get also some assistance with the architectures, because it's not very standardized how these architectures are being written. And if I want to compile, for example, for a MIPS 32, little endian, soft flow support, it starts, and in this already cached the build chain already, so it's already downloaded, and then it just built this, and it reused the old build cache to just run this. But then you say, yeah, it's already the build cache used, but we can also do a custom compile with another tool. To make integration of custom tools a bit easier, I integrated a custom tool here, so you can just add your own C code without having to interact with the toolchain. And we can, for example, instead of writing this here, we can do. And basically, this custom tool is being used kind of like canary on platforms. So it's just used if I don't know if the tools are running properly on the platform, I use the custom tool, which uses some of the functions of the platform to test if the compile was correct. So this custom tool is on the one hand kind of a test tool to test if the compile was successful. On the other hand, easy to adapt if you need to compile something without touching the build chain. So we can use the same command and just use the command now -d or -f to force a rebuild. So, and now it really built the binary again. And then on the output and the target architecture, we have now the binary. So we have here the custom.muscle. It always names the binary after the build chain it was built with. And you see nearly all binaries are built with muscle. And now in the system, we could use, for example, QEMU to test if this is really working. MIPS. I hope we have QEMU on there, which works. Let's test it out. Output, nope. MIPS, and custom. So, and it really works. So it is a valid MIPS binary, which is now compiled, for example, with the custom code. And you could just use this, for example, to replace this with anything you want without having to edit the build chain yourself. But adding the build chain isn't that hard because it has like a decent design which reuses a lot of functions. So when we take, for example, a look at a script, how this is being built, we can, for example, look at, how curl is being built. And we see here, for example, you just need to define where your binary is coming from, and also there's like the SHA-5 hash is being or the SHA-512 hash is being pinned. So if curl would be compromised, it would be noticed at this point. And then you just have to say create build dir, get the output path, and then you can just use some library functions that are being used in the tool, say download and extract. And the thing you have to do is like get the compiler flags from the tool, and then you can just do the configure. And then this is like a custom part you have to define. How do you want to configure your tool? What dependencies do you want to use it? And then, yeah, curl has a lot of options. And then you just say make, and it automatically builds a tool for all these architectures then. So writing the scripts is rather easy, I would say. But if you don't want to write the scripts, you can just use the example custom code and just adapt this. Okay, so that was it for the demo for usage. Well, but it's all just bash script. So it's easy to hack around, and you should be good with just some bash script knowledge. Okay, but which tools did I include, and why did I include them? BusyBox. BusyBox is kind of a no-brainer, because BusyBox is like the core utils of all kinds of contains, like the quality utils, all kinds of Linux tools that you can use. For example, it contains netcat. It contains, for example, a small HTTP server, FTP server, which is nice for transferring files. And it just makes usage a bit easier because most target systems have a small BusyBox install with many tools, many features disabled. And here is a full BusyBox install with all the features. And I also made a patched version of BusyBox because when BusyBox gets a SUID bit, it drops it on most shells. And the BusyBox no-drop version basically makes this that if you have, for example, a SUID bit set on a BusyBox binary, it doesn't drop it if you enter a shell. Okay, what else do we have? Shells. There are some predefined shells on there, like reverse shells and different shells, for example, that can be used in different approaches. For example, if you have the need to do a shell that, for example, loads a script or just executes a bash script, the shell helper would be cool, and also the classic binary reverse shell. And also these shells are compiled as LD preload libraries. And for example, a few weeks earlier, at the beginning of October, I think, for example, I used one of the shells to exploit the sudo chroot exploit with these shells because on an embedded device, because the tool already compiled the shells for this target platform. Okay, for product assessments, I often have to look at TLS configurations and want to break up TLS configurations or TLS settings. And the problem is, like on embedded systems, there's not just OpenSSL, there are many different TLS libraries. There's Wolf SSL, Embed TLS, and some other libraries. And I wrote also a tool that's called TLS Preloader. It uses LD preloading, which is a technique to override functions in Linux, to just disable TLS validation on all kinds of libraries. So I use this a lot for testing, for example, what does a client send to the cloud, what data is being transmitted, and this is also integrated into tooling. Okay, and also the classics like strace, ltrace, and gdbserver, which are very useful for reverse engineering and dynamic analysis. Strace and gdbserver are quite easy to build, however, ltrace is like really tricky to build. And I generated a chart for this to explain why, for example, ltrace is so hard to build. So, to get ltrace, the following build steps were needed. So, basically, if you want to build ltrace, just an example why is it difficult to compile stuff. You need all these libraries. Setlib is not hard to compile. libm and libpthread come from a libc environment. If you use musl, bad decision. You need to build elf utils first. However, elf utils uses a lot of functions that are, for example, just in the glibc library, for example, argparse or argp. And also some other functions which allow you to get information about the stack. So first you have to compile all these libraries, then you get elf utils binary with musl, but however this elf utils has still some bugs, so it doesn't compile directly, so you have to introduce some custom patches. And these are basically because most of the constants in there, which are, for example, registers, for example, magic constants, are based on glibc, and they're lacking in there. So we need to introduce them via some custom patches. Then we get elf utils library, a static one. However, ltrace, by the way, if you have used ltrace before, ltrace is like the prior release was 2013, and there's a new release from last week. So maybe it's time to update the ltrace because now it has better support for more modern architectures like Long Arch and some other architectures. And also RISC-V. So, and however, here is the same problem. Some registers are missing that are being defined by glibc. So I had to write a lot of custom patches to get it to run. And in the end, if you just want to include a custom library for demangling, that's okay. And then you get ltrace binary. There's a lot of hoops to jump to. And you could have said, I could have just used glibc. But well, I decided to use musl anyway. And yeah, but now I have a working musl build with ltrace. Okay, some other tools in there, NCAD, socat, nmap, why not? And also microsocks, which makes your socks proxy, and curl is in there. Okay, and as I mentioned before, you can just add custom tools yourself, either via replacing the custom binary or the custom example tool, or just registering your own build script. Okay, some real stories. Okay, in the beginning of this month in September, I was with some colleagues on an assessment of a solar park. And normally the solar parks, they are like classic OT systems, so they are during operations, they should not be interrupted. And we had the issue that we needed to verify who had access remotely to the solar park, because it wasn't like clear which subcontractor had access and how the remote access is working. So after some reconnaissance, we got access to like the gateway of the solar park. The gateway was like a LTE modem with some switch ports at the bottom. It was just like a classic modem. And the problem is like we couldn't just unplug it, so we had to do, and we weren't able to intercept any kind of LTE traffic or see what kind of connections are coming in there. But at some point we got the root shell, and however the operating system was quite limited, so there wasn't anything on there that was useful to track the connections that were going across the router. However, we had the toolchain, and we built just tcpdump for the target platform, put it on there, let it run, and then we had full access to the traffic that was going across this router. So sometimes these tools can be quite useful because it was an on-site pen test, and it's rather uncomfortable when you're on an on-site pen test to start messing around with compiler flags and GCC. And the tool basically saved our day. And during abandoned pen testing, it's also quite useful because it makes your life just easier. So it brings all the tools you probably need for dynamic analysis and some basic reconnaissance. Okay, I brought a live demo, a real router. So bear with me if this works. Okay, here I have a classic OpenWrt router. So it's just, if you log out again, it's just an OpenWrt router. It is a MIPS-based router, and I will now try to infiltrate some tools in there and show you how this can be used. So I have here, okay, I already pre-built the binaries because if we would build them now, it would take like a half an hour, so I already pre-built them. So, but if we, for example, we can now use, for example, our busybox for our own server and use the muscle version. And for example, busybox has a small HTTP server included. So, sorry, I use. So if you zoom out a bit here, so it already brings a small HTTP server, which you can already use, for example, to transfer files. So you can just type -f to keep it in the foreground, -f, and then just serve the home directory of the other binaries for the target architecture. And then we are good to go. Okay, rest is in use. So let's use another port. So use just 1, 2, 3. Okay, so our server is running. And now we can just use here, because here tools are quite limited. I do not have many tools on this platform yet. And what's interesting is like the memory on the system is quite limited. You see, for example, the ROM is like only 4 megabytes, but there is a lot of storage in the temp directory. So you will use that to just transfer some tools. And now, for example, I can use wget and use wget and download some of the binaries. It's the 2, I think. And just use the busybox muscle for the target architecture. Just going to check it. Seems like we didn't connect the network. Give me a second. Network's there. Just 1 second. It should be all there. Yeah, it seems like we have a network issue, but we can just switch to the desktop version of it. So in the build folder, you now have different shells, the different tools. And for example, what I can show you is, for example, microsocks, which is a cool tool, which is basically just a socks proxy with like, I think it only has like 16 kilobytes. Yeah, and it's basically a small micro proxy that allows you to spawn as a socks proxy. And for example, now we have a socks proxy running on our system, but it would also work on the target system. And for example, we could try to, for example, use this via Coemo now. That's something we could do. So if you just do it like this. Okay, so the router setup is somehow not working, so I'm just using Coemo here to emulate this. But if you, for example, just compile it and just use socks now, for example, oh wait, I forgot the port. Wait, it's closed already. Oh, did I? Let's give it a second try, and then we should be. That's not working. Just give me a second. It's there, or did I mistype it? There we go. Now it's at least using the proxy. I don't have internet in the frame. Okay, so for example, now the proxy is running, it's trying to connect to it, and it also worked now. For example, it tried to do a curl via the proxy we emulated for the MIPS architecture. And for example, this microproxy is quite nice because then you can, for example, pivot across routers or, for example, different network devices with the setup. And we also have some other tools in there. For example, the ltrace version, which is quite useful if you want to trace, for example, sys calls for different binaries. So now you can just not trace sys calls, but function calls. And here we see, for example, now we see all the kinds of libc functions that are being used with ltrace. However, not every binary that's being in part of the build chain is building for the target architecture, because that heavily depends on the tool itself often. Because some tools have some dependencies that do not work well on every platform. For example, ltrace is a good example. ltrace relies on ELF utils, and only on the target architecture that's supported by ELF utils, these binaries are being run. Okay, just let me check. Something else interesting I'm going to show you. Okay, let's keep going because we are already out of time a bit. Okay, so that was it for a short introduction to Sthenos. In general, if you have the need to compile embedded tooling, which is based on C and C++, please give me a call. I'm interested in what kind of binaries you're using for embedded pen testing, and maybe if we can extend this tool to be more fitting for my general pen testing purposes. And I'm also trying to test this on more real hardware and more devices. So because like in Coemo, it's rather easy to test something because it's easy to set up, but I noticed that some architectures are not supported in Coemo and are hard to test without proper hardware support. Okay, so and the next milestones for the project is more testing. And also I want to rebuild Nmap to be more portable, because Nmap is not very portable at the moment because it lacks all the service probes. And there are so many patches and quirks in all these kind of tools and combinations with certain architectures that need to be patched. And maybe I want to build a gdbc with strace. Okay, so that's it about Sthenos. I will just go back to the QR code so you can scan it if you want to.
Any questions here in the room, or maybe in the streaming room? I take silence for a no. So with that, we can conclude there's a coffee break or a beer break below until 4 o'clock, and then we're back here. And give another round of warm applause for Felix.